Hello everyone. So in this video we're going to be looking at proof by induction. So we have been given a very interesting question to prove by induction, and generally to prove anything by induction there are 3 steps in which we need to follow. The step 1 is called a test case. Now when we talk of test case, the test case here we have to assume that it is true for the lowest values of n and k. So it means we are going to assume it's true for n equal to 1 and assume it's true for k equal to 1. Now the second step that we need to look at, step 2, is called the inductive step. Now for the inductive step here, we are assuming that it is true for a certain value of k that is found in within the range. So we are going to assume here that it is true for a certain n equal to k, where this k is within our range. K belongs to the range of our function. And for the third step and the final step, step 3, which is called applying, here we are applying the inductive hypothesis. So we want to apply the inductive hypothesis. So in this step, what we need to do is we simply use the assumption in step 2 to prove true for n equal to k plus 1. So if our conclusion will simply be that if step 1, step 2 and step 3 are all true, therefore it's true for any n or for any k. So let's look at it properly. Okay, now we're going to go for step 1, the lowest values of n. That is when n equals to 1 and when k equals to 1. We want to show that this particular step is true for both equations. So we have this, and we have this. We need to show that when k is 1, the right hand side is equal to the left hand side. So if we substitute that here, therefore we are going to have the sum from k equal to 1 to 1 of 2 into 1 minus 1 all that squared should be 2 into 1 into 2 into 1 minus 1 into 2 into 1 plus 1. Now all of this divided by 6. So we know that this is 2 minus 1, which is 1, equal to, here is 2 into here is 1, and there is 3 divided by 6. So clearly this is 1. So here we know that since 1 is equal to 1, it's true. So we have proven for the lowest case. We could go further and prove for n equal to 2, and obviously k should be 10. So let's go ahead and prove. You can do that for so many cases. Let's assume now that n is 2, right? And for n equal to 2, we're going to substitute it here. So to do that, we're going to have 2 times 2, which is 4. Now 2 times 2, 4 minus 1, 3. And 2 times 2, 4 plus 1, 5. Now divided by 6. So this will be 1, this will be 2, 2 go here. So this will be 10. Now how are we going to show that 10 is equal to what is on this other side? So when we look at the individual terms, is actually the sum of the squares of all the odd numbers. So to get the second term where n is 2, we simply need to sum the first 2 terms of the squares of the odd numbers, meaning that we're going to sum this, right? So this will be equivalent to 1 squared plus 3 squared, which will be 10. So it shows that this is true for n equal to 2. So obviously it will be true for n equals to 3, true for n equals to 4, and so on. So it will be true. And for each time that we change our n to the next number, we make sure that we are going to add the numbers, not just take the term individually, but we'll add the numbers. So as an assignment or an exercise, I want us to look for the corresponding value of this expression when n is 3. So let's put our solutions in the comment section. So I will take a look at that. So good. After proving that, like, this is our first step, proving that okay, it's true for all the test case. After proving for the test case, we're going to go to the hypothesis case. Now for the hypothesis case, step 2. Now for step 2, which is a hypothesis case, we are going to assume here. So we are going to assume this is true for a certain value of n equal to k. Now this is an assumption, right? So meaning that we have the sum from k equal to 1 to k of 2k minus 1, all that squared. Now this will be equal to, so since our n is equal to k, we're simply going to replace anywhere we see n, we replace it with k in this our expression above here. So to do that, we're going to have 2k into 2k minus 1, 2k plus 1. Now this will be divided by 6. Now that's what we have for step 2. Now for step 3, which is the inductive hypothesis, we're actually applying the inductive hypothesis. Now for step 3, the inductive hypothesis. So here, so the inductive hypothesis. So here we are going to use the assumption of the inductive step to prove true for n equal to k plus 1. So we are going to use the assumption above here. We're going to use the assumption above here to prove true for n equal to k plus 1. But to do this, we need to take note of something. If we look at this, our expression above, we see that we're adding 1 squared plus 3 squared plus 5 squared plus right up to for this case, let me take for instance for this case, for n equal to k, meaning that we're going to add this expression right up to 2k minus 1, all that squared. So if we assume that we're adding up to the term n equal to k plus 1, therefore we're going to have another term here, which is the term plus 2 into k plus 1 minus 1, all that squared. So this is a very, very important step in our proof. So let's look at that in practice. So to do this, we first of all have to come up with our general term. So we have 1 squared plus the next term was 3 squared plus 5 squared, and so on until we had n. Let me verify that. Okay, we had 2n minus 1, all that squared, so which was equivalent to the sum from k equal to 1 to n of 2k minus 1, all that squared, equals to something. Now we are going to come to that. It's not really important right now. So the most important thing is for us to look at it here. So we are going to have 1 squared plus 3 squared plus 5 squared, now right up to, so we are going to have 2k minus 1, all that squared, so plus 2 into k plus 1 minus 1, all that squared. As I said earlier, this is a very, very important step. This is k equal to 1 to k plus 1 into 2k minus 1, all that squared, now equal to our expression above. Now this is a very, very important step. I want to reiterate on this because now let's look at what happened here. So if we let's look at this term. Normally the sum from k equals to 1 to the k plus 1 term is simply the sum of the first n term plus the n plus 1 term, or the k plus 1 term. So that is the whole idea behind this particular expression here. So that is the whole idea behind this expression. But having this, we need to equate it to what we had above here. So to equate that, I think I need to create some space. So that will be equal to, so anywhere we see n, we're going to replace it with k plus 1, right? So we're going to have 2 into k plus 1, so into 2 into k plus 1 minus 1, and let me create some more space. 2 into k plus 1, so plus 1 divided by 6. Now let's come back to this expression here. If we look at this from here up till this level, we see that this is the sum from k equal to 1 to the power k, right, which was step 2 of the in the inductive step, right? And we actually assume that this inductive step was 2k into 2k minus 1 times 2k plus 1 divided by 6. So this step here, that is what we meant by assuming the inductive step to prove for the inductive hypothesis, meaning that we're going to use the assumption above here to prove for this, and that is exactly what I meant when we said the first time we are going to use that assumption. So if we do that, instead of having this term here, we're simply going to replace it with this, and it's all going to make sense right now. Now let's look at it together. So meaning that at this point, I'm going to replace this with 2k into 2k minus 1 into 2k plus 1, all that divided by 6, right? Now plus our n plus 1 term, as I explained earlier. So it will be 2 into k plus 1 minus 1, right? So all of that will be squared. So this will be equivalent now to this our expression here. So this will be equivalent to this our expression. This will be equivalent to this our expression. So this will be equivalent to 2 into k plus 1 into 2 into k plus 1 minus 1 into 2 into k plus 1 plus 1. So all of this divided by 6. Good. So this is already good. So what is left for us to do now is to show that this statement is true, meaning that I want to show that the left hand side is equal to the right hand side. So we are going to go ahead to simplify this equation, and to do that, it's simple. We just have to see how we are going to manipulate with the various terms. So to start doing that, we are going to have 2k here into 2k minus 1 and 2k plus 1 divided by 6. Now we see that 6 is in the denominator and also 6 is there. So in order to create 6 here as well, we're going to have since we have 2 here, we want to create a 6 here, so we're going to have a 6 divided by a 6. So we haven't actually changed anything. 2 into k plus 1 minus 1, all that squared. Now this again, we haven't changed anything, since 6 divided by 6 will be 1 times this remains with that. So this will be equal to what is above here. I really don't want to copy it, I'm just lazy, but we need to have it in mind that that's what we have. So meaning that 6 is going to cancel through outright. Now this is what is going to happen. 6 is going to cancel out here, 6 is going to cancel out here, and also this 6 is going to go away, meaning that we are going to be left with only the numerator, noting that a 6 has been added here. So if that's the case, then the next step we simply continue with our simplification. So we're going to have 2k here, and we're going to have 2k minus 1 and 2k plus 1 here plus, so we are going to have 6, as I said. Now we will have to expand this function. To expand this, we're going to have 2 times k, we're going to have 2k, 2 times 1, we're going to have plus 2, right? Now plus 2 minus 1 is going to give us plus 1, so that will be all squared. Okay, great. Now we want to look at the ways in which we can simplify this term. So to do that, we are simply going to see we have 2 into k plus 1 here. Okay, here, right, we have 2 times k. We're going to have 2k. I don't know, right? So we're going to have 2k. 2 plus 1, we're going to have 2 minus 1, so we have plus 1. Okay, great. The same thing here, we're going to have 2k, right? And 2 times 1, we're going to have 2 plus 1, so 3. So plus 3. Great. So it's like divided by 1, which is still the same thing. So this is what we have. Apparently this is what we have. Now we're going to realize something. We have the term, well, we have a term. We have the 2k plus 1 term here, 2k plus 1 term here, and 2k plus 1 term here. But we have 2 of them since it's squared. So we're going to cancel that out, meaning that we just have to simplify our results, right? So here we're instead going to have 2k into 2k minus 1. Now since this is going to go away, it will go away with one of these and also with that, right? So we'll be left with plus 6. I don't know why this thing is disturbing, but we'll be left with 6 into 2k plus 1. Remember that it was squared, so when we cancel 2k plus 1 all through, we'll be left with one term. So this will be equivalent to 2 into k plus 1 times 2k plus 3. So that's 3. Good. So everything is boiling down to something reasonable. Now we just have to continue simplifying this. So to continue our simplification, we have to multiply this. 2k times 2k will give us 4k squared. 2k times it will be minus 2k, and here we're going to have plus. This will be 12k plus 6. Good. So this will be equivalent to, now this is like 2k, right? This is like 2k plus 2 now times 2k plus 3. k plus 3. So to do the multiplication here, we'll have 2k times 2k will be 4k squared. 2k plus 2k times 3 is going to be plus 6k, and 2 times 2k will be plus 4k. Oh my god. So this will be plus 4k, and 2 times 3 will be plus 6. Now what do we realize? To further simplify this, we have 4k squared. Now this will be plus 10k plus 6. Now this will be 4k squared plus 10k plus 6. Interesting. So we realize that, okay, the right hand side is equal to the left hand side, meaning that this term is equal to this term equal to this term. We can boldly cancel that out. We can boldly cancel it out. So we can boldly cancel this term out, right? This is gone. We also have 10k equal to 10k here, meaning that we can equally cancel that out, and 6 equal to 6. We can equally cancel it, meaning that 0 is equal to 0, which is true, right? So once we have this, we have proven our we have shown that the above hypothesis is true. So therefore our conclusion will be that it's going to be true for all n. So basically that is proved by induction, and the good thing about proof by induction is that once you're able to know how to prove this by induction, just following these steps, any question that comes will follow the same steps throughout. So you'll be able to do this for all proofs by induction once you're able to once you're intuitive enough to know how to manipulate with these terms. So basically that's it. And on a serious note, I really wish to plead for your support. I'm still a new YouTuber and I'm also a student, so it takes a great deal of sacrifice for me to sit down and create a video. So I really plead for your support. by subscribing and liking my video. I'm still a new YouTuber, and like my videos are always lost within the pool of millions of videos on YouTube. So for you to support me through this my journey, just please click on the subscribe and the like button, so that at least my videos can be shown to more audience that will need the content. So hopefully see you in the next video, and if you have any video idea or any topic in mathematics, just feel free to share with me. I'll be very happy to make a video on that. Until then, see you in the next video.